Welcome to Planet X421ZZ, or Planet X for short. On Planet X, student teams collect robots through a visualization system they build as their final project. This game, that we call Roboviz, is joint work with Elsie Lee Robbins. We've been running a version of it in our graduate course for 2 years with nearly 100 students. Roboviz is an alternative to traditional final projects and information visualization courses. Final projects, which are often open-ended, are a core part of most InfoViz courses. We have surveyed many such courses and have found final projects to be ubiquitous. In theory, these projects are a great idea. They allow students, usually in teams, to practice and develop their practical information visualization skills. They also give instructors a way to assess learning objectives. Unfortunately, the problem we've encountered with open-ended projects, or even slightly less open-ended ones, is that they often focus on what we call visualization-adjacent skills. These are parts of the process that are important, but not necessarily a key part of a visualization curriculum. Usually, teams have to find a good client or problem, collect data, clean it, determine tasks, and only then actually build the visualizations. If they get lucky, the first parts of this process are relatively easy. Students can concentrate on building the visualizations. We as instructors get to evaluate how well students learned InfoViz theories and how well we taught them. If students get unlucky, they may spend all their time trying to isolate or clean the data, find tasks, and so on. The result is that they haven't really leveraged what we teach them about InfoViz. We can't guarantee that they'll have an interesting data set, good tasks, or a wicked design problem that actually challenges them. Even if one team gets lucky, others won't, and the result is unequal learning and assessment. We'll come back to this, but our focus is on core visualization curricula. The other aspects of the process are important, but we don't want them to damage our pedagogical goals. Speaking of, our learning objectives are that students will be able to apply good design practice to generate and contrast design alternatives, document and justify design decisions based on visualization theory, implement functional and usable visualization systems, select and utilize appropriate encodings for a range of data types and design tasks, implement appropriate interaction techniques and visualizations, apply good design to produce aesthetic visualizations. To achieve these objectives, we created Roboviz. Students spend the first 7 to 8 weeks of class learning theories of visualization, seeing examples, and learning how to implement visualizations. After this, we challenge them to build a visualization system for real-time gameplay. While students don't actually have to compete, we offer a tournament at the end of the semester for students to test their creations. Various milestones and a video report are collected to assess learning. Roboviz has a somewhat complex set of rules and data elements. These force teams to trade off different strategies and make hard decisions about which visualizations they actually want to implement. Teams of 3 to 5, which is our usual team size, can't really build a solution that does everything. The game works something like this. 2 teams land on Planet X and are tasked with recruiting robots left on the planet by a past mission. The 100 robots left on the planet have different levels of productivity in mining the resources of Planet X. Teams have 100 Planet X time units, which is 10 Earth minutes, to recruit the set of robots into their teams. The team that collected the group with the highest productivity wins. Students are told that the robots have been previously abandoned and want to make sure that they only join a team that's on the same wavelength as they are. To determine this, each robot plays a guessing game with the 2 teams. We call this the friendship game. The robot thinks of a number, and teams have to guess that number by a certain time in the game. For example, Pushwalker Botson may be thinking of the number 34 at time unit 73. Teams are also informed that the robot's number isn't completely random. Robots use some complex function, maybe something like a 4th-degree polynomial, to generate the distribution for all times. This way, if teams can somehow collect samples from this distribution, they will be able to make a better guess for a robot. The data for the friendship game is the first data type we have in Roboviz, a time-varying one. Each robot has a different time series in mind. However, these are not completely independent. Students are told that robots were self-replicating and could produce child robots on the planet. Robots would inherit and slightly mutate their time series based on their parents. The result is that robots that sit near each other in the tree, like siblings or cousins, tend to have more similar datasets. Strategically, robots with lots of siblings or children may be more valuable to try and model. Doing so requires visualization of a different kind of data, a hierarchical one. A third kind of data in Roboviz is a network, specifically a social network. Robots on Planet X have a friendship network, Where this becomes important is in situations where two teams guess really close to each other in the friendship game. In that situation, the robot won't know who to pick and will speak to their friends. The more popular the friend, the more influence they will have. So if our robot pushwalker can't decide, they'll consider where their friends went. In this case, they would join the red team. But here they would join the blue. Finally, remember that we said that robots have different levels of productivity. In fact, some robots may have negative productivity. To determine this, we tell students that robots are composed of parts. For example, they might have a polarity sink or a nanochip. Parts are a combination of quantitative and categorical. For example, the polarity sink might have a quantitative frequency of 7.3, but the nanochip may have 3 models, alpha, beta, or gamma. Although the teams don't have these values, we randomly assign correlations between the part values or types to productivity. A robot's overall productivity is then based on a function of these parts. If a team can determine a robot's part values and the correlation of those to productivity, they can focus on better robots. A subtlety of the friendship game is that a team can guess a value of -1 if they don't want a robot. This can help them avoid getting a bad robot on their team. Teams are given the network and family tree data at the start of the game. However, the time series and robot data come to them a little by little over the course of the game. Part of the game mechanics is a hacker living on the planet that leaks information to the teams a little bit at a time. Every Planet X time units or 6 seconds, teams get a few time series data points and a few parts for random robots. However, part of the game and the strategy is that teams can ask the hacker to focus on a specific robot or specific parts. Teams can bias their requests toward things that they actually care about. For example, those robots that need a guest soon or have high influence in the social network might be more interesting. Each 10-minute match is completely different from the previous one. We generate an entirely new family tree, a new social network, and an entirely new set of friendship game time series, and a new set of correlations and weights for the parts. A good visualization needs to support many different instances of a game. Data distributions change, as do the shapes of the networks and other objects. We can also change the importance of different strategies. For example, we can change if on average a robot is likely to be productive or unproductive. Teams that only try to collect the most robots in one game will find the strategy to work against them in another. Teams are required to make decisions based on only what they see in the visualizations. They can't use ML or statistical tricks to figure out what to do. A good design will allow a team to decide which strategy to emphasize, what to guess, when to do it, and what to ask the hacker. Again, the rules are somewhat complex and the full details of all this are in the paper and supplemental site. Teams build their solutions use a variety of libraries, but mostly using Altair and Streamlit. These are covered at the start of the semester. We also give them access to simulated game servers, some API code in Python and JavaScript, and a simulated opponent that can extend. We've run the game for 2 semesters with 10 to 11 teams each time, and the results have been highly encouraging. At the end of the semester, we let teams play over a knockout-style tournament over 1 to 2 days. Again, this is optional, and teams can earn a tiny amount of extra credit for playing, but not enough to influence their grades. Our grading rubric, which is also available in the supplement, is aligned with the learning objectives. Most teams score full points for aesthetics, justification, and functionality. We find the largest deductions were due to the interactivity features and suboptimal design choices. Interestingly, most of these suboptimal choices were due to teams resisting editing down or removing parts of their visualizations that weren't actually helpful. A second benefit of the rubric was that it allowed us to identify limitations in our teaching and change the course. For example, this year we hope to focus more on implementing interactive features and critique visualizations with extraneous features. The result we are most excited about, however, is the diversity of visualization types created by each team. In the past, it was unlikely that a project would have a network, multivariate, hierarchical, and temporal components all at once. We find much broader coverage when using Roboviz. Specific distributions and examples for these visualizations are available in the paper, but here are a few examples of visualizations created by students. We view Roboviz as an overall positive in meeting learning objectives and giving us the ability to provide assessments. However, we recognize that we are applying a specific learning philosophy that comes at some cost of realism and responsiveness to student interest. To address this somewhat, we've allowed teams with strong visions to pick their own projects. However, only 2 teams have taken us up on this offer over the 2 semesters. Another type of limitation we have identified is that teams rarely build novel encodings that combine data types. For example, we did not see some novel combination of the network and time series into one visualization. This was due in part to the incentives we applied. An instructor that finds these novel encodings important can modify the grade structure to reward them. Other modifications might add or remove data types based on materials covered in class. For example, one could add a text component and remove the hierarchical data. Again, a broad discussion of modifications and limitations is available in our paper. We hope that others find inspiration in the idea of using this kind of game structure in their course. We're also delighted to open source the tool to any instructor who wants to try it in their class. Feel free to reach out with questions.